Well, we finally made it to the transmissive segment, the last part of the neuron. We're ready to see how this neuron communicates with another cell. So this whole picture that we're looking at is a synapse. A synapse is where the neuron is going to communicate with either another neuron or the effector. And it does so by secreting neurotransmitter. So let's start by labeling some parts here. This area right here on your synaptic knob is the presynaptic membrane. So remember, this whole structure is the synaptic knob. We labeled those when we first labeled the neuron, and its membrane is called the presynaptic membrane. And one of the important features of this membrane is that it has a negative charge. And you'll see in a few minutes why that is important. Then over here, we have our postsynaptic membrane. This is the membrane of either the next neuron's receptive segment or your effector. Remember, effector is the organ that we're telling to do something. So this could be a muscle or a gland. And it could be skeletal, smooth, or cardiac muscle, any of the three. Then you have a gap between them here. This gap between them is called the synaptic cleft. So this whole area between the two membranes is the synaptic cleft. So pre means before and post means after. So the presynaptic membrane is before the synaptic cleft and the postsynaptic membrane is after the synaptic cleft. So information is moving this direction. Remember, information always moves one direction. So the basic idea, we'll do the basic idea first, then we'll get into a little more detail. The basic idea is that the synaptic knob secretes neurotransmitter. So that is the red dots here. These little red triangles are the neurotransmitter. The neurotransmitter diffuses across the cleft and then it binds to receptors. So these blue things here are ligand gates. So it binds to receptors on the postsynaptic membrane. And the receptors are part of the ligand gates. And then that makes these gates open when they do, ions move in and out. And then you have the signal. Signal is received. Okay, now we can look at a little more detail of how this happens. The more detail is in the form of control. How do you control when you release neurotransmitter and when you don't? The neurotransmitter, notice, is kept in vesicles. So these are vesicles that contain the neurotransmitter. Also remember that the receptive segment has voltage-regulated calcium gates. And that when they open, calcium moves in. These vesicles have a negative charge. So remember when I said that it would be important that the presynaptic membrane has a negative charge? This is where that comes in. The vesicles and the presynaptic membrane both have a negative charge. So remember, like charges, they repel, right? Opposites attract, likes repel. So the vesicles do not want to get near the presynaptic membrane. If they do, they're pushed away by that electrostatic charge. So as long as they're pushed away, they cannot secrete their neurotransmitter. So here, anytime if this vesicle were to get too close to the membrane, it would be repelled back away from the membrane. When you do want to release the neurotransmitter, so you've had an action potential, so these lines, these orange arrows, represent an action potential. If you're having an action potential here, that means you're raising the voltage. So that means up here in your axon, you're doing that whole sodium in, raise the voltage. And then remember, the sodium diffuses. And when it does, it also raises the voltage of nearby areas. So when the action potential gets down to the end of the axon, you have an increase in voltage right here. These calcium gates are voltage regulated. So that makes these calcium gates open. So when there is an action potential in the axon, it raises the voltage. This then stimulates the calcium gates in the knob to open. The calcium comes in. And when calcium comes in, it coats those vesicles. So here you can see, here's a vesicle coated in calcium. Calcium has a positive charge. So when it coats the vesicle, it makes it positive. Now that it's positive, it is attracted to the presynaptic membrane because opposites attract. So now the vesicle will fuse with the presynaptic membrane and secrete the neurotransmitter. And if you remember from back in chapter 4, that is exocytosis. So now, because opposites attract, the vesicle and the presynaptic membrane are attracted to each other, and they will do exocytosis. And now that the neurotransmitter is released, it will diffuse across the cleft. It will bind to the ligand-regulated gates on the postsynaptic membrane. Then you'll get ions moving in and out here, and you will get a signal on the next cell. So that is how you transmit the signal from one cell to another. Now we have to look at what happens after the signal has been transmitted. You can't just leave that neurotransmitter in the cleft. So after the signal is transmitted, you have to clean up the neurotransmitter from the cleft. There's two ways to clean up that neurotransmitter from the cleft. This way is showing reuptake. So this is where you have transport proteins that will move the neurotransmitter back into the knob. The other method is down here, number 2. You can have an enzyme that breaks down the neurotransmitter. So right here, acetylcholine, ACH, is our neurotransmitter. So first it's released by exocytosis right here. It diffuses, it binds so that the signal is received. Then it comes over here and this enzyme breaks it. Here's the little broken parts. Then the broken parts do go back into the knob. But before they do, they're broken by an enzyme. So either way, you have to get that neurotransmitter cleaned up. You have to deactivate it so that it can't keep repeating the signal. So the purpose of this is you want to avoid repeating the signal. So that is why you will either take up or break down the neurotransmitter. Okay, then we do have neuromodulation. So neuromodulation is where you don't necessarily clean up the neurotransmitter right away. So in neuromodulation, you're going to alter what happens with the neurotransmitter in the cleft. Okay, and a lot of times you're going to act to keep the neurotransmitter in there so that you do repeat the signal. So an example of this is cocaine. You can see in this picture, cocaine has been added. Cocaine are these red things here. Here is that transport pump that will do reuptake of dopamine. Cocaine, notice, blocks this. So if you take cocaine, here's the normal situation. You release dopamine, it binds, then it goes back into here. So normal, here's the dopamine is released, it binds to the receptor, then it goes back, and you get that feel-good signal once. Right? Dopamine transmits a signal of feeling good. If you have cocaine, you release the dopamine, it binds, you get that feel-good signal, and then when the dopamine goes to go back, its way is blocked. It can't get back in to the synaptic knob. So then it bounces back and it binds again. So then you get another feel-good signal. And this just keeps repeating over and over. Every time the dopamine tries to get back into the cleft, the cocaine is there blocking its way back in, so it bounces back, binds to the receptor again. And then you repeat the signal. Another example of neuromodulation is with botulinum toxin. So let's review what goes on with a muscle. And we're going to put some ideas together from Chapter 10 and Chapter 12. So this picture should be familiar. Remember, the whole idea is that you get an action potential on your sarcolemma. That goes down the T-tubule. And when it does, you release calcium from the terminal cisternae. And that calcium, here's all that calcium. Remember, the calcium binds troponin. And that moves tropomyosin. And then you get cross bridge and power stroke, and the muscle contracts. Okay, so let's tie in some stuff from Chapter 12 now. Here is your neuron that's having the action potential. So we would have an action potential on this motor neuron. We get down here. Remember, we're going to let calcium in. It's going to make the vesicles turn positive. They're going to fuse with that presynaptic membrane. You get exocytosis. And in this case, that neurotransmitter that we're secreting is acetylcholine. Acetylcholine is the neurotransmitter that is used to stimulate skeletal muscles. The acetylcholine diffuses across the cleft. Here are the receptors on our postsynaptic membrane, and now our postsynaptic membrane is the sarcolemma of a muscle fiber. These gates open, they let sodium in, potassium out, and that creates an action potential on the sarcolemma. Then when you get over here, that action potential goes down the T-tubule. The terminal cisternae has voltage-regulated calcium gates. The terminal cisternae is just like the synaptic knob. The terminal cisternae has voltage calcium gates that open when there is an action potential in the axon. In the T-tubule. Just like the synaptic knob will open its voltage-regulated calcium gates when there is an action potential in the axon. So there's a lot of parallels here. You have an action potential in the axon, makes calcium gates in the knob open, and you release neurotransmitter. Over on the muscle, you have an action potential on the sarcolemma and T-tubule, makes voltage gates in the terminal cisternae open, and you release calcium. So back to the botulism and how this botulism is going to affect this process of the neuron stimulating the muscle. So let's think about botulism. It has become a lot more rare. But if you think about older people you've been around, maybe your great-grandparents, or if you work in a nursing home, do you ever notice they have this thing about dented cans? They don't want to eat food from dented cans. The reason for that is before we got better technology like we have today, you could get botulism in your canned food, and it was a type of food poisoning. So botulism, first of all, it comes from a bacteria, and this bacteria tends to want to grow in canned foods. Now, today, technology and sanitation have improved, and it's very rare you're going to go to the grocery store and get some canned food that has botulism in it. But years ago, before the technology was what it is today, you did sometimes get botulism in canned foods. And when the botulism grows in the canned food, it makes bubbles. And those bubbles can dent the can. And that's why people who are old enough to remember when you did need to worry about botulism don't like dented cans. It's a sign that it has botulism. So anyway, what happens is the bacteria makes a toxin. And this toxin from the bacteria gets into your synaptic cleft. And it blocks acetylcholine. So you cannot have the acetylcholine to stimulate your muscle. So back up here, where you're secreting acetylcholine, and that acetylcholine is binding to the gates on the muscle, that does not happen with botulism. So if you had botulism, you would not have this. So botulism causes flaccid paralysis. Your muscles can't contract. And this can be deadly because then you stop breathing. So now, your heart wouldn't stop beating. This affects skeletal muscle, not cardiac muscle, but you rely on skeletal muscles to breathe. So, although it's rare today to get botulism from your food, some people purposely inject themselves with it. That is the whole idea behind the Botox injections. It's a little bit of botulinum toxin, and the doctor injects that into a muscle and it paralyzes the muscle. And people do this. It can be used like to stop the wrinkles, because if you can't move the muscles on your face, you can't wrinkle your skin. It's also used for people who are having really painful muscle spasms. They can inject a little bit of the Botox in there and stop the muscle spasm and the pain.